so today I was gonna talk about series and a little bit more about conditionally convergent series. Right? So let's say conditionally convergent series. So this is a concept which is related with the order in which we add the terms of a series. So we have like A1 plus A2 plus A3 and so on. Most of the time here, when we talk about series, we understand infinite series. So the difference, if we have a finite series, we don't really have any problem with adding the terms in a certain order. So if we add A1 and then we add A3 and then we add A2 and then we add A4 and things like that, if it's a finite series, we're always going to get the same answer because of the properties of addition, commutative property and also associative property. As long as you keep the signs the same, you don't switch the signs, plus or minus, then you get the same answer. That's not the same thing with series, infinite series. So if we add them, we usually, when we write something like this, we usually understand this. And so on. So in other words, we add A1 plus A2, and then we add A3 to that, and then we add A4 to that, and so on. So what you're getting, so for instance, this one is usually called S2, this would be called S3, and then this would be called S4. These are usually the partial sums. So partial sums. So by definition, if this is convergent or not, it's related with the limit of the sequence of partial sums. So whatever this is convergent or is not convergent, that's going to be the meaning of the series, can be convergent or not convergent. But when we talk about conditionally convergent, that means summing them up in a certain order may affect the answer, may affect the sum of this. So this is usually called the sum of the series if it exists. If it doesn't exist, we don't really care about it. So conditionally convergent means that the order is important, but more precisely, if we put absolute values on top of this, we get something that's not convergent. So if you add them in a certain order, you get something convergent, but if you add them with absolute value, so just put in parentheses, absolute value of A1 plus absolute value of A2 plus absolute value of A3 is not convergent, so in other words, adds up to plus infinity. In other words, a conditionally convergent series is going to be a series where the numbers are not all of the same sign. Because if they're all of the same sign, absolute value is just going to be either the same thing or minus that. So then this is not going to be much of a difference between this and that. So that means you're going to have some changes in signs. So most basic example of something like this is the alternating harmonic series. So if we go from n equals 1 to infinity, and let's put here n minus 1, we want to start with plus, so it'll be 1 minus a half plus a third, and so on. So this is an example of conditionally convergent. Because what happens? If we just add them in, like we said here, we're gonna, I think I did show it in one of the videos in there, or I talked about it, is this is gonna sum up to ln of 2. But if we drop the signs, so if you just do 1 plus a half, plus a third, plus a fourth, plus a fifth, and so on, we get the harmonic series, which we know is non-convergent, which is like that. So this is usually called the alternating harmonic series. And if you drop the signs, you get the harmonic series. Harmonic series is divergent, it goes to infinity, but if you put the signs in, I mean the alternating signs in, plus minus, plus minus, plus minus, you get something that's convergent, and that converges to ln of 2. So I was gonna check that with Mathematica here. How do you type that in Mathematica? Just say sum, and then you put the negative 1 to the power k divided by k, or n, doesn't matter. And then add from n to infinity. And we get negative ln of 2. Why is it ln of 2? Well, because I've got to put here minus 1, right? We need to start with the plus 1, not with minus 1, right? So if you put here n equals 1, 1 minus 1 is 0, negative 1 to the 0 is 1, so you start with plus, minus, plus, minus. Whereas if you start with n, you're gonna alternate the signs by starting with minus, so that's why you get negative. So in other words, the summation of this is well known. Well, one of the interesting things about this series is that it's called Weierstrass theorem. Which says that if you have a, let's get rid of this. Oh, this is not working again. I don't know what's wrong with this thing. Not responding to this. If we have such a thing like a conditionally convergent series, so it's given a conditionally convergent series, summation of an, we can and given and let's say and some number, some real number, alpha. So it can be anything, 0, 1, 2, whatever, 7, including infinity and minus infinity, but that's not really important here. So then we can rearrange the order of an. In other words, we do a permutation of the sequence. So let's call that permutation, we call it Bn. then the exist Bn a permutation of An such that this summation is alpha. In other words, we can rearrange this, and if you do the sum in that new order, the sequence is going to converge to something that whatever we will pick from the beginning, like a magic trick. So like a magician work, so you give me a number. It's at 7. Okay, so I take this series, put these things in a different order, and I get the answer to be 7. This is kind of surprising, right? Pretty surprising. But let's look at some example with this series. And let's suppose we have picked, instead of ln of 2, let's pick half of ln of 2. In other words, alpha. I'm going to pick alpha in this case to be half of ln of 2. So this series converges to ln of 2, but I'm going to rearrange the terms, and we're going to get the answer to be half of ln of 2. Of course, if this order wouldn't have any role, this will give us a contradiction, because you're summing up in one order, you get ln of 2, then you're summing it up in a different order, you get half of ln of 2. That's completely, contradiction. But the contradiction is not contradiction because the order is actually important. So let's reorder them the following way. So I'm going to add 1, and then subtract 1/2, and then subtract 1/4. So let's put them in order here. 1/2 plus 1/3 plus minus 1/4 minus 1 plus 1/5 minus 1/6 minus 1/7
plus 1/7
plus 1/7 minus 1/8 and so on. So notice, so I put this in here, and then this in here, and then this in there. So notice now 1 negative 1/4, instead of being the 4th now, is the 3rd. And now we continue with this guy, 1/3. And then notice the pattern here. We add one unit fraction. This is usually called the unit fractions, or sometimes they're called harmonic fractions. It goes back to the Egyptians, because the Egyptians, they like to work, when it came to fractions, they like to work with unit fractions. In fact, they had all this system of measurements in which the measurements were all built as unit fractions. So they had, now if you go to a store, an old-time store, they have all these weights, and the weights are certain numbers in terms of the unit, kilogram or grams or whatever, but there are certain denominations, certain values. If you combine them, you can actually get any kind of weight you like. But they most of the time this is based on, writing numbers in base 2, base 3, base 4, base 5, 10, work base 10, right? But they didn't have that kind of concept, so they work with numbers like units. So 1/2, 1/3, 1/4, 1/5, things like that. And I don't know what it came from, but I think it comes also from the connection with music. Because when you play certain sounds, like 1/2, 1/3, 1/4, in terms of the length of the string, you get something that sounds harmonious. But if you play something that it's not a fraction like this, like 1/√2, it's gonna sound really, really bad. It's not gonna sound nice. So this fractions comes, is probably the connection. I mean, this was known to the Pythagoreans long time. So it was, you know, Egyptians and the Pythagoreans don't seem to match that much. But so the next one will be 1/3, but then notice the pattern. We subtracted 2 even ones. So the next one will be 1/6, and then next one will be 1/8. So bring this one in, and then bring this one in. Now you can guess what the pattern is. So the next one is what? 1/5, 1/5, and then minus 1. Notice that we finished with all the even ones up to here. So this is the next one. 110,
112.
and then 112. Right? Plus, what's the next one?
17.
17. And then the next one would be 1 plus 13 minus 1 plus 14 plus 1 plus 15 16. So we finish with this one. So the next one is
14, 16.
14, and then not 15, 16.
16, yeah.
Notice the signs are the same. We don't change. We don't change the signs. We just change the order. So let's recalculate now. Notice that this is a shift. This is a shift which is quite big, because notice what's happening with the first unit fraction in each one of this. We group them in 3 right now. And then what happens with the first? It's all the odd, right? All the unit fractions with odd denominators. But look at the last one. 4, 8, 12, 16. So notice what's happening. It's 1 times 2 is 2, so this is a little bit more than that. 3 times 2, 6. A little bit more than that. And then 5 times 2, 10. A little bit more than that. So basically, it's a huge shift, because you're going from 1 unit fraction to twice the one. So it's a huge shift, because notice that if we just shift them around in small areas, that's not going to make any difference, because we already know that the addition is associative. So we need to have something that kind of moves farther and farther and farther away in order to change the summation. And that's what's done here. So now let's add them up. So how much is this? 1 minus a half is a half. And a half minus a fourth,
3.
it's a fourth.
Yeah.
Right? So this is 1/4. 1/3 minus a sixth. 1/6.
1/6.
Because you multiply this by 2.
Yeah.
The 2 minus 1 is 1, so 1/6. And then 1/6 minus 1/8. How much is 1/6 minus 1/8? 1/6 minus 1/8 is what? Bring it to the same common denominator. So this multiplied by what? 3, and this multiplied by 4, right? It's the other way around, right? 4. 6 times 4 is
24.
24. 3 times 8,
24.
24. So 1 over
24.
24. the next one? 1, 5 minus 1, 10 is what?
110.
Well, let's not add them all together, just add the first two. So one minus a half is 1/2, minus a fourth, so let's leave it like it is, the same thing here. 1/3 minus 1/6 is 1/6, minus 1/8. So I'm not gonna add those together, just leave it like it is.
Okay.
So 1/6 minus 1/8 plus 1/5 minus 110 would be 110 minus 112. And then 1/7 minus 114 is 114 minus 116 and so on. What do we notice at this point? The denominators of all these unit fractions are 2, 4, 6, 8, 10, 12 and so on. Which means they're all the even ones. Well, if they're all the even ones, I can factor a 2 from all of them. So this is gonna be 1/2 times 1 minus a half plus a third minus a fourth plus a fifth minus a sixth and so on. Well, but this is exactly what we started with, which is the same. So this is gonna be 1/2 times ln of 2, and that's the alpha. That's we picked. Now, there are various examples like this. I think that one is in the Stewart textbook. So it's a good idea to look at that one. So now the question comes, how do we know that this sums up to ln of 2? Let me erase that. So now, remember when we started the class, we talked about Riemann sums. And then we look at some limits. And we say, well, some of these limits actually can be reduced to Riemann sums. And then we calculate them using the fundamental theorem of calculus. But that's actually going back to that subject, going back to the beginning of Calc 2. So the question is, why is it that summation of -1 to the power n minus 1 divided by n from infinity 0, 1 to infinity is actually ln of 2? So let's look into this exercise that I think we did it at that time, which was this. Suppose we add 1 over n plus 1 over n plus 1 plus 1 over n plus 2 all the way to 1 over 2n. So we add all the unit fractions, but we don't add them all together like in the harmonic series. We just add a chunk of them. We add, let's say if we start with 3, we want 1/3 plus 1/4 plus 1/5 plus 1/6, because the last one will be twice as big. And then if we start with 7, it will be 1/7 plus 1/8 plus 1/9 plus 1 over 14. And then if we look at all these numbers, what do they approach? Well, it turns out that approach to ln of 2. And the reason is this exercise that we did at that time. We factored this 1 over n in front, and we get 1 over 1 plus 0 over n, right? 0 over n is 0. And then n times that would be 1 over n. The next one would be 1 over 1 plus 1 over n. Well, because n multiplied by 1 is n n plus one over n, and then multiply by n, will be n plus one, which is this time, and so on. So, 1 over n, 1 plus 2 over n, and so on. So now we rewrite it like this, but we observe that this is nothing else but if we consider the function f of x to be 1 over 1 plus x, this is f of 0, this is f of 1 over n, this is f of 2 over n, this is f of n over n. So in other words, this is just the average values of this function for the inputs 0 over n, 1 over n, 2 over n, all the way to n over n. So if you average the values of a function, that's really a Riemann sum. And the Riemann sum converges to the integral. So this converges to integral from 0 to 1. Right? This is 0, this is 1. That's the graph of that. 1 over 1 plus x dx. Well, antiderivative of 1 over 1 plus x is ln of 1 plus x. So now we're using the fundamental term of calculus, evaluate this between 0 and 1, and get ln of 2. So this is an exercise that we did at the beginning of the class. So now the question is, what would that have to do with this? Right? Let's look at some numerical evidence. Get this back again. Power on. Power off. On. Ah, here we go. So let's introduce the partial sums. So if I, instead of summing from 1 to infinity, let's sum it up from 1 all the way to, let's say, 2 times k. And I'm going to call this function s sub k. So s sub k is the partial sums, but we add, we go all the way to some fixed number, which is 2k. So if we're going back to this picture over here, calculation over here, if k equals 1, for instance, we stop at so 1/7, negative 1/6 plus 1/5, negative 1/4 plus 1/3, negative 1/2 plus 1. So if let's look at the values of this function. Now what's s of 1? S of 1 is 1/2, which is this 2, right? Now what's s of 3? Well, 2 times 3 is 6. That means, no, so this is s sub 1, and s sub 2 will be all the way to here. Right, 2 times 2 is 4, so we stop at 1/4. So let's see how much that is. S sub 2, 7/12. Well, let's see if that's correct. 1 minus a half is a half. 1/4 minus a fifth. No, 1/3 minus a fourth. 1/3 minus a fourth, bring it to the same common denominator, will be 1/12. So S2 is 1/2 plus 1/12. The least common multiple is 12, multiplied by 6, 6 plus 1, 7, so that's 7/12. That's exactly that. Let's see what the next one is. So S3, 37/60. Well, we need to add these two together again. We need to keep on adding this next two together. Well, 1/5 minus 1/6, well, bring it to the same common denominator, it'll be 6 minus 5 over 5 times 6, which is 30. So then it's 1/30, so plus, so S3 is 7/12 plus 1/30. What's the common denominator? 60, right? So multiply this by 5 and this by 2. 5 times 7, 35. Plus 2, 37 over 60. That's exactly this one over here. So notice that if we keep on going, we get some partial sums. These are not all the partial sum, but the sum. Well, in general, if you have a sequence which is, if you have a series in which the series is convergent, doesn't matter what sequence or partial sum you take, should converge to the same thing. That this is true for any convergent sequence. If you take a convergent sequence and you look at the subsequence is still going to converge to the same limit. So in other words, you're basically deleting a bunch of terms of the sequence. So the rest of the sequence, as long as you have infinitely many, they're still going to approach the same limit. That's kind of easy to see. So, but now let's look at this sequence. So let's introduce this sequence in Mathematica, and let's use a different letter for the function. Delete. I'm going to call this S or T. T of K. By the way, this is the syntax to introduce a function. So you have K is a variable, and then colon equal is to define your computer science, so you're used with that, right? So, so I'm going to use the same notation as before, summation 1 over n, and then n is going to be running from 1, not from 1, from k to 2k. I have too many brackets. Okay. So notice that the first unit fraction that we add is 1 over k. The next one is 1 over k plus 1. So let's change this to k. So 1 over k, k plus 1, k plus 2, and so on, k, 2k. So this is my t of k. We know that the sequence converges to ln of 2. If we show that this sequence and this sequence, the ones we had earlier, they have the same limit, then we got. So let's look at some of the numerical evidence that we have for this sequence. What's S of 1? What's T of 1? It's 1/2, it's K is 1, so it'll be 1/1 plus 1/2. Because doubling 1 would be 2. So this is what? 3/2, right? And then, what's T of 2? One over 2, and then 1/3, and then 1/4, because double 4 would be 4, double 2 would be 4, so that's the last one we have. Well, let's add these fractions. What's the common denominator?
6, or no, 8?
No?
No, 12.
12. Multiply this by
6.
6, multiply this by
4, 3.
4, and multiply this by
3.
3. Okay, so if we add them together, what do we get?
13 over 12?
How much?
13 over 12?
13 over 12. Well, that's kind of close to what we did earlier, right? S1 was 1/2. S2 was 7/12, right? And so, what's the difference?
Is that numerator value?
And look, the denominator is the same, right? What about the numerator? We have, so this is 1 plus 2 over 2. So that's 1/2 plus 2 over 2 is 1, right? What about here? 7 plus what? 6 over 12. So 7/12 over plus 6 over 12, right? Which is 1/2, right? So if we actually get rid of this first term, that would be 1/2. If we get rid of this first term, it would be 7/12. Because 1/2 is this one. So let's see if the next will work. So T of 3 is what? 1/3 plus 1/4 plus 1/5 plus 1/6. We need to stop here because 3 times 2 is 6. So leave this alone. We don't get that into the calculation. And now let's add these 2 together, these 3 together. So multiply this by what?
No, it'd be, so it'd be on 60.
Yeah, so the denominator, the least common multiple is 60, right? So this one multiplied by 10, this multiplied by 12, right? And this multiplied by 15. 15 plus 12 plus 10 is what?
37.
37. So this is equal to 1/3 plus 37 over 60. Which means it's 1/3 plus S of 3. This is 1/2 plus S of 3. S of 2. And this is 1 1 plus s of 1. So let's see if this actually is true for some big values of s and big values of t. So let's look at s of 10, for instance. It's a huge number, right? And t of 10. Now the difference between them should be 1 over 10, right? So let's do the difference between these two. So t minus s of 10. 10. So basically we have, notice that the difference between them is first is 1, then 1/2, 1/3, 1/4, and so on, which is the first term in this sequence. And so if we drop this term, all these other ones add up to the same value. Which means if we show that this is actually true in general, it's just showing that this sequence has the same limit as this partial sums, because they are the same sequence. Because this part, 1 over k goes to 0 clearly. And so this is the identity that we need to prove. Identity. 1 minus 1/2 plus 1/3 minus and so on plus 1 over 2n plus 1 minus 1 over 2n. Notice that this is nothing else but s n, because we stop at 2n. And this is going to be equal to 1 over n plus 1 plus 1 over n plus 2. Notice I skipped the first one. That's not going to be in the calculation. Plus 1 over n plus 3 plus and so on. Well, if we prove this calculation, this converges to the sum of that series, alternating series, and this is a sequence that converges to the integral of 1 over 1 plus x, which is ln of 2, which shows that this converges to ln of 2. So that shows that this series, alternating harmonic series, has the sum, which is ln of 2. Now, why would this be true? You have to look to see what happens if we get to the next step. When assuming that this is true at any point value of n, we can actually get it for the next level. And we check it for the level 1, we already checked it for level 1, 2, 3, we checked it all the way to 3, right? And yeah, assuming that is true for some value, is going to be true for the next one value. So this, I'm going to leave you this as an exercise. This is usually called mathematical induction. This is a principle which is very important in mathematics because it assumes that if you have something true, it's like the domino effect. If you have something that, let's say you have a sequence, an infinite sequence of dominoes, and they're at the distance apart, each one of them are a distance apart, that if you push one, it falls on the other one, and it knocks you down. So the principle says this: if you knock the first one down, everything is gonna fall down. Well, the same thing here. If we check it for the first step, and then we prove that at every level being true implies the next level is true, then it must be true for everything. So that's called the mathematical induction principle. Notice if we go to the next level, we need to drop this term and keep on adding all these things, but we need to keep on adding the next term, which is 2n plus 1, and then plus 2n plus 2. Because this is a double of that. But if you subtract, so whatever we had earlier, and if we add this 2 and subtract that one, that's exactly what the next term is. But then you can combine these two. If you combine these two, it's 1 over 2n plus 2 plus 1 minus 1 over 2n plus 2. And that's exactly what the next two terms in here are. So the next level, you're adding this 2. And the next level here, you're adding this 3. But these two are the same. So each level you're adding quantities that are equal. And then, so if it's true at the beginning, it's gonna be true all the way to infinity, which means this is the summation. This is an elementary proof that this summation is actually ln of 2. So now it full circles back to the beginning of the course. Now there are some other rearrangements of the harmonic series that will give you some other values. One interesting thing here is that a rearrangement to give you a certain value is not unique. It would have been nice if it was unique, because in that case, we have a way to write the real number as a harmonic, as a rearrangement of the harmonic series, which would be really interesting, but that's not true. So, a good question here is that suppose you want to rearrange it to get your preferred number, let's say 1. How can you rearrange it to get 1? Because of the fact it's not unique, you may ask some other properties of the rearrangement about, so what is something that will make the rearrangement unique? This is a permutation of natural numbers, right? So I guess you can ask some questions, some conditions of minimality for the series. In other words, you look at the terms of the series, which is 1, 1/2, negative 1/2, 1/4, 1/3, negative 1/4, and so on. So then you may say, okay, there exists a rearrangement for which this is infinity. This gives you 1, the summation is 1. But then you want to be unique, so then you say, okay, I want a rearrangement in which 1 appears on the smallest position possible. And then the half and things like that. So you want to have something kind of to forces this numbers to be, in a sense, in a certain position. Anyway, so I think this is more like more to think about it and investigate a little bit more. Maybe I'll post some paper out there about this kind of topic. I'm pretty sure that people already talk about this and try to move a little bit farther beyond. I mean, this topic is it starts with that theorem of Weierstrass, but in some particular cases it can be actually a pretty interesting topic to study further. Okay, so I'm gonna stop here, and I was thinking to put the final. Nobody's probably gonna work on the final during the holiday, right? So I'm probably gonna put it next week.
Okay.
So in the meantime, try to do all the assignments, quizzes, and homework and everything, and that'll be the end. Okay, good. See you some other classes. Right?